All these lectures are kind of long. But so remember that this was our processor, and we added a couple neat things to it, right? We've really bolted on a few additional capabilities. We started saying, you know, a little processor with 8 memory locations is nice. I can do things with it, but I'd really like to be able to write programs with loops, and I'd like to be able to access more memory. So we added branching support. That was our branch logic, and you can see that the program counter is now fed by a multiplexer so that we can either increment the program counter or we can load an address from the instruction memory for a branching address, so we can do things like that. We added a larger memory, and we renamed our small memory registers. And this is an extremely common thing on virtually all processors, is that they will have a register file with anywhere from, let's say, 4 all the way up to 192 or more registers. And you tend to see more registers on RISC processors and fewer registers on CISC processors, because CISC processors don't really need them as much. And we had 2 different architectures we discussed. We discussed load store, which is kind of but not quite what we have here, because you can see that we also have multiple operand types, and you can just tell by looking at what feeds into the A argument to the ALU that we have a multiplexer there, and we can control that with a mode value in the instruction memory. So this is the multiple operand types approach, or the CISC approach. The load store approach is simpler, but it means your programs have to do more work to retrieve values and then manipulate them and write them back. So this is what we talked about last time. And we can implement programs that are now interesting. So we can do multiplication. We talked about that last time. This was the simple multiply algorithm that we looked at how to implement, and this was the assembly code, because we're not doing this in machine code right now. That would be too tedious. But this is the assembly code that we would have for our multiply operation. And as we look at this, we think, well, multiply seems like a useful thing to be able to do a lot of. I'd like to be able to use multiplication in my other programs that I write. So now we're going to get even slightly more complex and implement discriminant. So this is going to take 3 arguments, A, B, and C. They're all integers because we don't want to talk about floating point. We basically only talk about floating point in the first assignment, and then everything else after that is pretty much ints all the way through. So discriminants, we take A, B, and C, and we just compute b squared minus 4ac, and we compute b squared as b times b. So clearly we need to use multiply a few times in here. And like I say, we know that we can implement this in our instruction set because we already know how to implement multiply. And the only other things that we really have are subtraction. We can do the 4 in a couple of ways. We could either call mul again with the constant 4, but we all talked about how this is actually a little bit slow, so we'd rather just shift it left 2 bits, and that'll be identical to multiplying it by 4. But you can see that we need to call multiply twice, and this is where we have a little bit of a difficulty. If we were really naive, we could just plop the multiply code in twice. In fact, that's what modern optimizing compilers will do sometimes, because they say, ooh, this code is short, and to avoid the overhead of calling a function, I'll just plop in the code for this short function call. That would definitely be one way of doing it. But we're not obviously talking about that right now. We're talking about how do we actually implement this concept of a subroutine. The obvious thing that we need to know, the most obvious thing I should say, is how does multiply take its arguments and where does it return its result? And we already had this little convention, it wasn't a very complex convention, that we're going to pass arguments as the low addresses, or registers 0, 1, 2, as many as we need. In this case, we only need 2, so registers 0 and 1. And the result will always show up in the register with the highest index, or R7. And so, ideally, we just put the values in, like we'll put B and B into R0 and R1. We'll invoke mul, and out will come b squared. But then we run into this more serious difficulty, which is how do we actually get to mul and then get back? And we have this BRZ thing, but the issue is that we call mul twice. And the first time we call mul, we need to go back to where it was called the first time. And then after that, we need to call mul a second time from a different location in our code, and then we need to get back to that second location. So we have this challenge that we don't know how to get back to where we're called from yet. And you can see that we're going to have to change the processor design to do that a little bit. Now, one other question. I say here that we need to know how we take the arguments and how the values are returned. We need to figure out how to get to mul. We need to figure out how to get back. Is there anything else in the picture we need to think about? Hint, what registers are we using so far? We've talked about registers 0 and 1 and 7. But mul uses other things, right? We also need register 2 for our temporary value, so we can do a bitwise ANDed with 1 over and over again. And 3 and 4 are going to be constants. Well, maybe what we'll do is we'll be more clever, and we'll start encoding constants into our programs. That'll at least free up registers 3 and 4. But you can see that right now, we only have registers 5 and 6 that are available. Or maybe, if we're really nice, registers 3 through 6. So whatever the calling code is, if it stores values in these registers, it's going to be really sad. So now we have a coordination issue. We have this subroutine, but we have to treat it like a clear box because the subroutine uses registers that we may also want to use, and we need to make sure that we don't allow the multiply code to trample on our work. So these are the 3 problems that we need to solve, and I'll just re-enumerate these again. So a way to pass arguments and return values between the call and the subroutine, a way to transfer control to the subroutine and then back to wherever it was called from. And then we also need to be able to isolate the subroutine state from the caller state. And you'll see that the first issue is one that we can just design around. And that's what you generally notice, is that you pick a convention and then you use it everywhere in your program. And it's a convention. It's not like a fundamental principle or a truth as the way that you must pursue this. It's just, you pick a way of doing it, and then everywhere you have to use the same way. That's another one of those things about why we sort of require 32-bit Linux for this class, is that Unix-based systems use a calling convention called cdecl, which you'll learn a lot. You'll probably be sick of it after a little while, and then you'll start to be really comforted by it because it's cool. Windows has another one called standard call. They're slightly different. They're very similar, but they're slightly different. As long as everybody uses the same calling convention throughout, you have no problem. So that's one of those things. You just sort of come up with a design and then you stick with it. The second and third ones actually require more design, more hardware support to actually be able to implement them properly. We just don't have the capability yet. Okay, so we have this program. We need to invoke mul twice. And jumping to mul is easy enough. We could just say brz 0, mul, and we would get to the multiply function. That's fine. But like I was saying, getting back is the hard part. And I'm just going to cut to the chase so we don't have to belabor all this. We cannot do this with our current architecture. Why not? Well, look at our brz instruction. I can only hard code an address into the branches 0 instruction. I can't give it a register or some other indirect value. This is another thing you'll notice. We talk about abstractions. We want to build a good hierarchy of abstractions where each layer completely obscures the layer beneath it. That's a really powerful way to approach things. So far, we haven't successfully done that with subroutines because we still have to know about the innards of the subroutine. But you'll also notice another really common principle in software engineering and in computer science in general is that we keep adding these little layers of indirection. That's another really common theme, and we're going to talk about it more in a future lecture. But here we have a literal address that we encode in our branch of 0 instruction. Well, that's powerful. We can do certain things, but what would be even better is if we could also replace that with a name, a variable, so that we can pass in whatever value we want, and then we can have the brz thing go to the right location based on what the variable contains. That's indirection. Okay, so here's our logic, and you can see that right now our design just simply doesn't support taking an address from a register. Right now, you look at, okay, where do the wires go? The wires go either from the instruction memory into the program counter, or they go from the program counter plus 1 into the program counter. So that's really the problem. We're going to have to change this logic here. And then once we can do this, well, we'll do something that's not very nice, but we will pass the return address to go back to into in another register. And then our subroutine, when it's done, we will use that register to go back to the caller. Does this make anybody feel slightly dirty? It definitely makes me feel slightly dirty, the idea of passing a branching address in a register and hoping that the subroutine doesn't have any bugs where it gets trampled or you end up in la-la land or something like that. But anyway, this is what we're going to do. This is the updated logic, and you can see now, again, we're bolting this on. We don't really design processors this way in real life, but we're just bolting onto our existing work. We have the register B. We'll bring up a line from that and go into our multiplexer, and now I can either have a branch address from the instruction memory go in, a value from the B register, or program counter plus 1. And we add another branch mode to the instruction so that that can control where the branch address is actually taken from. Okay? So this is a way that we could solve this problem. Now we have enough capabilities to actually implement subroutines. And so this would be what the branching logic might look like. So the opcode is BRZ, register A is 0, so branch if 0 is the value 0, yes, okay. If the branch mode is 1, then take the new program counter value from the register, otherwise just take the branch address from the instruction memory. Really simple, right? There's not really much complexity here. And now we can actually use multiply as a subroutine. You can see that we have these parameters, so registers 0 and 1 are A and B, our values that we're multiplying together. 7 is still the output, and 6 is this crazy thing where we go back to. Where was multiply called from? And so we end up with code like this. We say move ret into R6, where ret is an address. And you can see that we're also, I think I have a note about this, we're introducing a move instruction just to simplify our code. You can see that you could implement move with add if you just put a value and 0 together and then store that into a register, but who wants to write silly stuff like that? So we'll have move. We'll move the return address into R6, and then we will call mul, and when it comes back, we know that the answer will be in R7. Okay? So this is the way that we can do this. And if we have multiple places that we call mul, well, we'll just have multiple return labels. We'll move those label values into R6, invoke mul, and we know it'll come back to the right place. Okay, so here's our discriminant function. And again, we say, you know what? I don't know why. Maybe we're writing a program where we need a lot of discriminants computed, but we say, it'd be really nice to have this as a subroutine as well. And so we say, you know, I'd like to pass A, B, and C as our register values, and then it needs to do its work and return its result somewhere. But the problem is now the discriminant's really getting crowded. It doesn't actually have that much work to do. It just needs to invoke multiply twice and then shift and answer left 2 bits and then subtract the 2 things from each other and return that value. But multiply is getting really beefy as far as its register requirements. We have A, B, and temp, 1 and 0, address 5, register 5 is the only one available, and like I said, maybe we could just hard code our values 1 and 0 into our program, since we're starting to move toward a CISC architecture, and that would free up 3 registers, but that's still really a big pain. And we start thinking to ourselves, well, if I have this subroutine, then really I'd like to use it as a black box, not as a clear box. I'd like to not care what is in it. I'd like to have some inputs that go into one side of the box and out pops the answer. And I don't have to think about the machinery inside. That's abstraction. I like to not think about that stuff. I'd like to think about my problem. So can we come up with a way of changing this so that we no longer have to care about what data subroutines need to manipulate and how much storage space they need and so forth? Okay? Like I say here, this is really all we'd like to think about. How do I pass arguments to the subroutine, and how do I get the return values back? That's really all I care about. And then we'd like the subroutine to be able to do whatever it wants. If it needs to use all the registers, fine, I don't care. If it needs to use one of the registers, fine, I don't care. You may have a situation as well where a subroutine runs out of register space, in which case, if it has a way of squirreling those away somewhere and then fetching them back, then that would be nice as well. And so this is where we can introduce the notion of a stack to use in this subroutine abstraction. And you'll notice that using a stack for this data structure, that you could use probably other data structures as well if you came up with a clever design, but stacks are really nice because it enables things like recursion, which we don't really go through in detail how recursion works in lecture, but you'll get an opportunity to look at that in the next assignment and see, when I have this nice subroutine abstraction, recursion just falls right out of it. It's so easy. It's so straightforward. Okay, stacks are last in, first out data structures. Think of it, you always put something onto the top of the stack, and the top thing is the thing you can access. And when you want to remove stuff, you take the top thing off, then the next thing off, and next thing. So that's why we say last in, first out, as opposed to first in, first out, and so forth. There's various different kinds of data structures. So we have a region of memory, which is the stack itself. This is where the values go. We have a stack pointer with the invariant that the stack pointer always points to the top thing on the stack. So the stack pointer always points to something. If the stack has any data in it, the stack pointer points to the last thing pushed onto the stack. That's a very important constraint. We have two operations. We have push, which adds something to the stack. You can see that in our way of designing it here, stack pointer is decremented, and then we put a value at the address that the stack pointer holds. So SP is an address. SP becomes SP minus 1, and then we store the register value. Pop, we do the inverse. We pull the value out of the stack that SP points to, and then we increment it. Okay? This is all we do with push and pop. Once we have this stuff, and also the nice benefit of indirect memory access, which we'll visit in a moment, then we can use this stack very effectively for implementing subroutines. Now you may be asking, why in the world does Donnie have this thing growing down? Why not just say SP is SP plus 1 or something like that? And that would be really nifty because then your stack pointer would also tell you how many elements are on the stack, and it would be really cool. If SP was 0, you could say, oh, the stack is empty, blah, blah, blah. The problem is the way that processors work. And I want to make sure to introduce this notion to you in the way that processors generally work so that it's not confusing when you actually encounter it. So stacks tend to be high in memory, and the stack pointer moves downward as you push things onto the stack, and then it moves back upward as you pop stuff off the stack. It doesn't really matter which way the stack pointer moves, as long as you have a notion of, well, is the stack empty or does it have things on it? Does SP always point to the top thing on the stack? So, but that's what's weird about it, is that the top thing on the stack will always be at the lowest address, which is kind of bewildering, and the bottom thing on the stack is always at the highest address. I apologize, that's just the way that IA32 works. Okay? Any questions? Just keep in mind, SP always points to the top thing on the stack. If you keep that in your head, you'll be pretty good. So once we have this stack abstraction, we can start using it to implement subroutines. We're going to continue to pass arguments and return values by registers for now. We will alter this slightly as we go through this. The subroutines can save and restore registers on the stack so that if I need to use all but one of the registers, like multiply currently does, I can save the old values, and then I can restore those old values at the end of my subroutine. So the subroutine has to respect the fact that this is a shared resource. The subroutines are responsible for using it and then restoring it to the state that it was when it found it. So this would be a way that we could do that. Notice I want to use R2, that's where I compute A ampersand 1. So I push R2, I do my stuffs. You can see that now we're encoding literal values into instructions, so that's kind of freed up R3 and R4, which used to be 1 and 0. And at the end, when I'm finished, I pop the old value of R2 off of the stack back into the register, and then I go back to whatever address R6 was at. Okay? So this is a little bit cleaner. Now, discriminant can be implemented without having to pay too much attention to what multiply does internally. It just has to pay attention to where do the arguments come in, where does the answer come out, and where do I store my return address. Okay? Little bit cleaner. Still not great, but a little bit cleaner. So this is our discriminant function. And like I was saying, we can think about the registers that discriminant might use for its argument. So A is going to be R0, B is R1, C is R2. And the result is going to be computed into R7. So this might be what we do. Remember, we have R0, R1, and R2 are A, B, and C. So I need to compute B squared first. I might as well. So I save A, because I need to set R0 so that I can call multiply. I set R0 and R1 both to B. And I tell the multiply function, come back to ret1, that address. And then I invoke multiply. And when it comes back, R7 is going to have the answer. So you can see that I restore A. You know, I have to make sure my pushes and pops match up. They're okay so far. So push R0, pop R0, so I restore A back. I push R7 because I want to save my B squared value. Yes, I'm okay so far. So then I move R2 into R1. So remember, R2 is C. I move that into the second argument for multiply. I say, come back to ret2 when you're done multiply. And then I invoke multiply. And I'm multiplying A and C together. Then I need to restore B squared. Now notice I pushed R7 before. There's no requirement that you must pop into the same register that you pushed from. Now obviously that constraint is there sometimes. Like when we saved R2, we needed to restore R2. But here, we're just using the stack to store a temporary value. So we pushed R7 and we popped it into R1. We shift R7 left 2 times to multiply it by 4. We subtract R1, or I should say we subtract R7 from R1, and we store the answer into R7, and we're finished. Okay? Does that make sense to everyone? This is how this code works. And you can see that, like I say, it is easier because now we have less things to think about. And we computed B squared first. I already talked about this. We saved the result of the first multiply and then popped it into another register that was more suitable. If we'd popped it back into R7, we would have overwritten the result of computing the multiply of A and C. But you can see that it makes it a lot easier to manage these intermediate values. Okay? So that's all fine and good. But we can use a stack for other things as well because we're still taking up quite a few registers just to pass our arguments and our return address. What is up with that? Passing the return address in a register as well. We had this code that you would notice every single time. Move ret1 R6 and then BRZ 0, again Y, and then jump to the multiply function and it'll come back to ret1. What if we could package those last 3 lines into some operation? So we don't have to do that every single time. We still have to set up the argument somehow. You can see here that I say we can pass those on the stack as well. There's no reason we can't. So we have this new operation call, which basically does the same thing as those last 3 lines. Call adder pushes the program counter of the next instruction onto the stack. Why does it push the next instruction? Well, because when we return, we don't want to go back to the call again and then call it and return and call it and return and end up in a loop. So we push the next instruction's address. And then we set the program counter to be the address that's part of the call. And then we have return, which takes whatever the address is on the top of the stack and stores that into the program counter. Okay, so you can see it pops and sets the program counter. That's what ret does. And it will go back to whatever address is stored on the stack. And so that means our code suddenly gets a lot cleaner. I love it when code shrinks. It's one of my absolute favorite things in the whole wide world. So we can get rid of these 3 lines. We can replace them with 1 line now. It could just be call mul. Off we go. So this will be the new strategy. You can see we're refining this progressively. The caller is going to push the subroutine arguments onto the stack, so we'll have to talk about how to get at those things. Then it will use call to invoke the subroutine, call mul, for example. The subroutine can use the stack for any intermediate values it needs to store if it runs out of registers, or if there are registers the subroutine needs to preserve on behalf of the caller. And then the subroutine will use ret to get back to the caller. So how does the subroutine actually access its arguments? Because it used to be that they'd be passed in registers, but now we're going to have something like this, where instead of saying, well, I've got to save R0 and then move R1 into R0 so that both R0 and R1 are B, I need to just push B twice and then call mul. So this is what the stack is going to look like. Remember, it throws down. I have B, and then I have B, and then the call pushes the address of the next instruction onto the stack, and then that's what return would use. So you can see that indirect memory access becomes very, very important because that's the way that I can refer to B, or the other B, and not have to pop everything off. This is the way that I could access these function arguments. SP plus 2 is going to be the first argument. SP plus 1 will be the second argument. Okay, which again, this is just the way that this is another convention where the first argument is pushed first. We could push the last argument first. We could certainly do that as well. So what would be the alternative? Well, if you were to look at this, you could say, well, I could get at those B's if I first pop off the return address into some register, and then I could get at the B's. I could go ahead and do that, and then I'll try to make sure to set it all back up the way it was when I was called, push the B's back on or something so that the caller can get rid of those, and then set the return address so that the ret will work properly. You could see that you'd start getting into some really serious issues then if you started taking that approach. So we keep it simple. You guys have people heard of the KISS principle? Keep it simple, stupid. And I use that for myself. I'm not saying you're all stupid, but we certainly have the capability of expressing unbelievable stupidity sometimes. So it's nice to keep things simple because then you sort of reduce your the footprint that your stupidity can hit sometimes. So anyway, it's just best to have simple designs. Now multiply does modify registers. I was mentioning before, R2 is used for A and 1. We have to compute that somewhere. R0 and 1 will be modified. So it'd be nice to push those things onto the stack as well, because I'd like to be able to have the caller think, I invoke this routine, and then I don't see any changes except for my answer shows up somewhere. So you'd like the caller to truly see the subroutine as a black box. But the problem is, as I start pushing things onto the stack, what's my access for B now? Or the other B? It used to be SP plus 1 and SP plus 2. But now it's changed as I've pushed other things onto the stack. Now it would be SP plus 5 and SP plus 4. You can imagine that if you were looking at generated code from a compiler, it'd be really bewildering as stuff is pushed onto the stack to see the indirect memory access addresses changing based on what's on the stack in between. How annoying is that? We don't want to deal with this. It'd be very difficult to write this code by hand. So what we do instead is we introduce this notion of a reference point into our computer. We call it a base pointer because it is the reference point for the subroutine to access its junk. Okay? So what we do when we invoke the subroutine, we set up this base pointer. And all we need to do is set the base pointer to be the current stack pointer, and then we can use that base pointer to reference everything else that's part of this subroutine's data. The only issue, of course, being that, well, if the function is invoked from another function, then the base pointer already had a value in it. So we need to save the old version of the base pointer before we set it to our reference point. So you see that the first thing we do is we store the old base pointer, and then we say base pointer equals stack pointer. The stack pointer points at the old base pointer. So now we have stuff looking like this. And then we can push whatever we want onto the stack. The stack pointer moves, but the base pointer stays in place. And we can now access things. We can access not just our arguments, but we can also access local variables using this reference point as well. So like it says here, argument 1 is at location BP plus 3. So BP plus 0 is the old base pointer. BP plus 1 is the return address, and so forth. So BP plus 3 is the first argument. BP plus 2 is the second argument. Okay? So we can update this. We're going to start actually having a BP register. So you can see that we push the base pointer at the start of our multiply function. We store the stack pointer into the base pointer. So now that becomes our reference point. And then all of our argument access is based on the base pointer. And so it'll look uniform within our subroutine. We save our registers. We start moving values into registers to do our computations. And at the end, we can restore the stack to the way it was when we were invoked, and then the last thing we can do is just ret, and it'll pop the return address off, and back we go. The caller will be none the wiser that we've been mucking around with all the registers. Okay, any questions on this? I know it's a relatively complicated thing to see for the first time. We're starting to have enough moving parts that it's kind of hard to keep track of it all. You will get very comfortable with this by the end of the term, I promise it. Because you'll notice that there's always the same prelude on every subroutine you write in assembly code, and the same postlude. It always starts, it seems, with push BP, move SP into BP. And at the end, you say pop BP, return. And that's all you do. Now this BP, this base pointer, we also call a frame pointer, because the subroutine takes a certain amount of space, it has a certain amount of data it has to manipulate, and that data that it manipulates we call the subroutine stack frame. Okay, so like I said, the stack frame is the portion of the stack allocated for a specific procedure call. And it's going to have all the state that's associated with that subroutine. We have the arguments, we have the return address to go back to, we have the old base pointer or whatever other registers we need to preserve on behalf of the caller, and we have any local state as well on the stack. And all of this is part of the stack frame for this subroutine, and BP is the reference point for it all. Okay, so that's why we call it the frame pointer. I guess I just said that. Okay, so any questions on this? This is why you will frequently see a BP register in many different processors, because it's a really useful abstraction to have for implementing subroutines. Or if you want to call them procedures or functions or whatever. I mean, the terminology changes from language to language. All right. Now, if you don't have any questions about that concept or those concepts, then we're going to start transitioning into IA32, because it's really gotten to the point where if we add any more complexity to the system, we might as well just talk about IA32. And then we can actually write real programs, not fake programs on a contrived processor that has to run on a real processor. Why not just program the real processor? So these are all the things that we have. Memory access, including indirect memory access, very, very valuable. Branching instructions, branch to register, or a way of jumping to an address specified in a register, more indirection. We have a stack abstraction and this notion of frames and frame pointers for implementing subroutines. So we might as well jump onto IA32. IA32 has 8 general purpose registers that we will care about. It has a lot of other registers for things like floating point and what are called SIMD instructions. We'll talk about some of those things in a second. Yes? Okay. Do you want me to go back a slide? Or? That is correct. Yeah. You will notice this about the stack. Stack management has to be a characteristic of the way you implement functions. There's not really much bookkeeping that goes into the system implementing the stack. The stack is a tool, and you have to write your code to use it properly. Compilers have to write their code to use the stack properly. So for example, you need to make sure that if you save some register because the caller expects the value to be preserved, you have to pop it off at the right place. You have to make sure that the number of pushes and the number of pops match up. You have to make sure that all of these things are done properly. So this is what you notice about compilers is they have a lot of bookkeeping to do just to keep track of all these things. The heap is very different. We haven't talked about the heap, but I'll just give you a little punchline. Where if you have to do your own memory management, then you have to allocate and you have to release, but the heap itself keeps track of what regions are in use and which ones aren't. And if you get to garbage collected memory management, then you have even less to think about. You just have to say, I want me some memory. And then you just stop using it and the system figures out that you're done with it. So, but at this very low level, there's a lot of things. You just have to implement them properly. And you have to think about, okay, I did these things, now I need to undo these things and make sure that everything matches up. Does that answer your question? Okay, cool. So, all right. Let us start talking about IA32. So IA32 has been around for a long time. Some of you have also heard the term x86, which is very true. It actually all started back in the 8086, which was one of the first processors in this family that I got to see and I got to play with. My first computer actually had an 8088 in it, which only had an 8-bit data bus. It was very limited. But anyway, yeah, so IA32 instruction set architecture for Intel Pentium family processors. And they are 32 and 64-bit processors. But they did start all the way back with an 8086, which was a 16-bit processor, and the companion processor to that, which was the 8088, which was an 8-bit processor. But it had the same instruction set architecture. So you can imagine on 8086, if you wanted to access a 2-byte word, it could do it in one memory access. If you wanted to access a 2-byte word on an 8088 processor, it had to do 2 memory accesses. They were cheaper. They tended to be in IBM PC clones, and that's why we got one. Okay? You'll also notice here, 16-bit processor, 29,000 transistors. That's a lot if you're doing this by hand. Thankfully, we don't. It is also very small compared to how many transistors there are now. Does anybody know how many transistors are on a current, like, Core I series processor, Intel processor? We're getting up in the billions, like maybe 2 billion if you're talking about a processor that does hyper-threading and multiple cores on the same processor. 2 to 3 billion transistors. That's a lot of transistors. But anyway, so we started with 8086, and the family has continued to develop over time. So you have the 186, which some of you have probably tinkered with in a 5X class. I don't know if you guys still... Do you guys do that still? Yeah, so I got to do that when I was an undergrad. We had 186s that we used. I also don't remember. Are they 186s or 188s? Yeah, so that's pretty awesome. It's fun to tinker with those things. They're simple enough and also sophisticated. I'm really glad that you guys don't use like a MIPS processor or something like that where it would be a completely different assembly language. There's a lot of good, sort of synchronicity between the classes so that you can reuse that information. So 386, 486, we get into 32 bits. 486 was the first processor with integrated floating point. Now, what does that mean? Before the 486, all of the floating point computations were emulated in software. It sucked. And so when I got my first 386, I actually saved up some money and I plopped in a 387 coprocessor, which could actually do all the math. And then my computer got a lot faster. It's crazy how things have advanced. You kids have it so easy. No, I'm just kidding. You'll be saying that to the next generations after you. Yeah. We were still limited to having 4 processors. It was crazy. So anyway, so Pentium 4, first introduction to 64-bit support. You start getting some really clever facilities starting to be offered on processors. We'll talk about a lot of those through the term. P4 was the first one that offered hyperthreading. Hyperthreading is basically referring to this whole notion of a superscalar architecture where you have multiple ALUs, you have multiple memory access units and so forth, and the processor is capable of scheduling instructions or parts of instruction execution on these different components on the processor so that you can get some overlap of the instruction execution. So they said it was kind of like having 1.5 processors available. Okay? on a good day. So let's see, hyperthreading, and then core 2 is multi-core, and then core i7 is multi-core plus hyperthreading. And there's many more very advanced facilities in these processors as well. Okay, now what's interesting is that they maintain backward compatibility all the way through, which means that when you boot up your awesome hex-core i7 with 3 billion gigabytes of RAM, it starts out behaving exactly like an 8086. You can only access 1 megabyte of memory, and the operating system has to go through and start turning things on because it knows that the processor can do a lot more. So it's one of those interesting little details. We talk about that a lot in the OS class because obviously that's a hurdle you have to jump over. Okay, registers. So we have 8 general purpose registers and a whole bunch of specialized registers we won't talk about. So you'll notice that we have bits 0 through 7, 8 through 15, that's the numbers, is how many bits or what bit indexes you have. And you have a register EAX, for example. Let me see if I have this here. You have a register EAX, and that'll be a 32-bit register. But you can also access the low 16 bits of that 32-bit register with the name AX, because that was what was on 16-bit processors. And then within AX, you could access the high byte of AX using the name AH, and the low byte of AX using AL. So if you modify AL, then you will see that change when you look at EAX. They're all part of the same 32 bits here. Okay? And all of these are the same, except that you can see that ESP, EBP, ESI, and EDI do not have this H and L thing. They just have ESP, SP, EBP, BP, and so forth. Okay, so ESP is the stack pointer. It is not extrasensory perception. And so ESP is automatically utilized for stack instructions. EBP is the base pointer. You can set this up and use it. You certainly don't have to. The compiler oftentimes will take a shortcut by not using EBP if it doesn't have to, and that's one less thing it has to think about. And then ESI and EDI are used for these string operations, which you will see like STOSB, that kind of stuff, LODSB. They frequently can be prefixed with rep. It's really weird. But the idea is you put the length of the string into CX and then call these operations, and they update ESI and EDI, do like a multi-byte operation. It's kind of weird. I haven't used those in forever. Okay, yeah, and so I already talked about this. Various widths of arguments you can utilize. And so if you had code all the way up to like 286, you would generally just use AX, BX, CX, DX, and so forth. Okay? And then when 386 came along, all of a sudden there was this EAX thing. And I honestly got quite scared because I was like, oh no, it's something new to understand. I don't like learning, it's scary. So, but, you know, it's just a really straightforward concept. There turned out also to be 64-bit registers. When we had the changeover from 32-bit to 64-bit, you also have RAX, of which EAX is the bottom 32 bits. So RAX is 64 bits wide, and so forth. Okay? You generally will not see the R registers in this class, just because we want to keep it simple. Now there's also other registers. You have EIP, which is the program counter, but for whatever reason, Intel decided to call it the instruction pointer. And eFlags, which is the flags register. So this is where the status values from the last ALU operation get stored, and then you can refer to them in operations as well. Okay, so EIP, 32 bits. There is also possibly the worst named register ever. RIP is a 64-bit register, so that you can have 64-bit instruction pointers. And like I say, you can't access the register directly. I want to change RIP. Here I go. I want to change EIP. Well, I have to call something, or I have to jump somewhere. That is how you set the instruction pointer. Obviously, it changes the value. If I want to read it, then what I can do is something clever like call the next instruction and then pop that value off the stack, because you could also use that to get at the current EIP if you need to. Okay, then eFlags is the flags register. We really only care about the carry flag, the zero flag, the sign flag, and the signed overflow flag. Okay? The direction flag is if you want to use those string move operations, the string manipulation operations. So carry flag is unsigned overflow. Zero flag is obviously if the result of the computation you just did is 0. Sign flag is just if it's 1, then the answer was negative, and if it's 0, then the answer was not negative, and the overflow flag is signed overflow. Okay? But there are operations that you can use for either looking at these things or jumping based on them or moving data based on them. There's a lot of really interesting things you can do. Okay? Let's see. Yeah, and there's a whole bunch of other registers which we aren't going to talk about. Take the OS class. You can see how these things now become a living hell for you. So CS, DS, ES, FS, and GS, and SS. Okay? Those are all 16-bit no matter what. You know, if you're running 64-bit OS, there's still 16-bit registers. There's not an ECS or an RCS or anything like that. You have floating point registers, which can do up to 80-bit floating point values. And then you have these other things, SIMD and MMX. And these instructions are very interesting because what they do is they take arrays of values and compute arrays of results. So in single instruction, multiple data. And MMX is just more SIMD instructions. MMX doesn't actually stand for anything, although colloquially we all kind of informally agree that it stands for multimedia extensions, but it really doesn't. It doesn't have a definition of what its name is. Okay? We will not talk about anything below, or actually anything on this slide in this class. Okay, let's see, word size. So usually, word size is what is the data bus width? IA32 makes our lives a little bit tough in this area because it doesn't really talk about that. In IA32, word size is what was the word size on the 8086? And everything is in relation to the 8086 word size. Okay? So IA32, the original 8086 word size was 2 bytes. Even on the 8088, you can see it started going off the rails really quickly. So even when you're on 64-bit, it's like, well, we're working with double word and quad word values, not words. You know, even though the processor is accessing 64 bits at a time or 32 bits at a time. So you have these terms: double word, 4 bytes, or 32 bits. And typically, int and long int will be those on GCC. I think it may actually be different in Visual Studio. I think long int might be 64 bits, but I don't remember. And then quad word is going to be 8 bytes. Long int. Like, long int is not enough. I need more long. So add longer to it. So let's see. Long int quad word for IA32 on GCC. Okay? Let's see. Now, when you have these multiple byte values, the order actually becomes important. Let's say that we had this value we were going to store. What's the most significant digit? 1, right? That's because we write our numbers left to right in English. So 8 is the least significant digit in this value. And so if we're going to store this, we have 2 choices. We could either store it with the most significant byte at the lowest address, which is comforting to English writers and other people with languages that go left to right because, hey, it's just like I read in real life. And then you have Little Endian, which is how IA32 does it, where the least significant byte is at the lowest address. So it would look like if you were dumping out memory, 78563412, which is bewildering. Okay? So you just have to think about these kinds of situations and how does the processor actually process everything. Okay? Intel is Little Endian. Various other older processors that thankfully aren't used very widely anymore are Big Endian. And then there's some processors that are able to do whichever you want. You can actually configure the processor in hardware to do either Big Endian or Little Endian. Now, obviously, when you build a computer, you typically pick one and use it. But some processors are able to do multiple Endianesses. Okay, questions? All right. Do people know where the term Big Endian or Little Endian comes from? Anybody know this answer? Yeah. Yeah, Gulliver's Travels. I can't remember what it was. There was like 2 warring factions, right? They had some people thought you should open the hard-boiled egg at the big end, and others thought you should open the hard-boiled egg at the little end, the pointier end. So that's where this term comes from. And it kind of speaks to the same holy wars that have been fought over whether processors should be Big Endian or Little Endian. I personally prefer Little Endian. I think it makes more sense. But It doesn't actually affect the hardware design much at all. Just affects data fetching. Okay, a few more things to talk about. The word size does have an impact on the system because it affects what a pointer can point to. So this is why I say here it affects how much memory the system can access. So if you have IA32, if you have a 32-bit processor, your pointers can have up to 32 bits. And so you can only access up to 4 gigs of RAM. Now, who here has a computer that has more than 4 gigs of RAM in it? So, for all of you, you couldn't use a 32-bit address, or else you'd only get to use the bottom 4 gigs, and the rest of it would be inaccessible. 64-bit processors can access a whole lot more. Now, like I say here, on IA32 or x86-64, our pointers are still not actually 64 bits. They're only 48 bits. So you have to go to other processors to actually access a full 64-bit address space. Now, 256 terabytes of addressable memory is still a lot of memory. So we're okay. Don't worry. We don't need to panic. But right now, on x86-64, you can only access up to 48-bit address space. So that's the nature of things there. Okay. Now, of course, that is what the processor imposes. The motherboard may have other integrated circuits that impose other constraints, or the motherboard itself may not run all of the address lines that you might want. So you might have a motherboard that's limited to 32 gigs of RAM, 16 gigs of RAM, or something like that. Okay? Like I am hopeful that in the next week or two I'll get to upgrade my laptop, and OS X is a 64-bit operating system, and the processor will be a 64-bit processor. But it will only be able to have 16 gigs of RAM. That's just all it can do. Okay. So pointers, if you aren't already familiar with this concept, are just an address or a location of a value in memory. And pointers do have a type. We'll be getting into that more and more as we go into these details. And you can see also the number of bytes that the value occupies is part of that concept of a pointer. Okay, let's see. Instructions. I think that what we're going to do is go ahead and wrap up here. I'll just throw this up here as the last slide. But what we'll do next time is we'll start talking about the nature of instructions on IA32, and we'll see how to write programs in it. So we'll see you all on Wednesday.